All right, day 3, you guys. This is nice. This is just going to be a one-parter. So day 3 is really going to talk a lot about the geometric power series, which we've discussed and we've seen, but we're really just going to focus more intently on it today. So we know that when we're looking at these series, we know that geometric, the endpoints diverge. And with ratio, we have to go and check the endpoints. So we're going to really start identifying when these are geometric. Okay, so here we saw this in the last notes when I was kind of challenging you guys a lot on those end problems, okay? But if I can see that I have this a over 1 minus r, then I can get that into the geometric power series. And here I know that whatever my r is, this is when we are going to converge, and that the endpoints are always going to have to diverge because that's where it would equal 1. And in geometric, when r equals 1, we diverge. So we never have to check them. So yay! Okay. So looking at this one, I can see that I have my a over my 1, and I don't have a minus, so I just got to go double negative to make that plus. So now I have an a over 1 minus my r. So when I do this, I can see my a is 2x, and my r is this negative x squared to the n. So if I'm looking for where I converge, now I'm looking for where my r value here is less than 1. Well, this is an absolute value, so I can get rid of that. And then we're going to use what we learned in that pre notes where we're going to bring this out and then take the square root of 1, which is 1. So here I can see that I have this now that I am centered at 0. This is my radius of convergence. Okay, I want you guys to try this next example. So I want you to represent this rational expression. That's what this is called when you have this polynomial over a polynomial. It's a rational expression. And you guys, they love to use that term. And when you see this term, rational expression, you should be thinking geometric, okay? Okay, so I have this rational expression, and I want you to rewrite that as a power series. See if you can do it. Okay, so this is what I got. So I'm looking for where my r is less than 1 for my radius of convergence. Cube root of 1 is still 1. Geometric at once now, let's see the interval of convergence. So I know I'm centered at 0. I'm going out to 1 and negative 1. And on geometric, they always diverge. Endpoints always diverge. Or you could have wrote it like this. Okay, so here is some function for g. And now it's going into power series and everything like that. But as soon as I see this, I know I want to go ahead and get this rational expression into a power series. When I see the word like series going on and I see this function, I know at some point I'm going to do it. So I'm just going to go get that knocked out of the way. So do that for me first. And they just use the variable t instead of x. That's fine. I mean, I don't really like it, but t's look like pluses, so I just try to make sure I have a tail on them. Okay, so here I can see I have this going on, and sometimes it's good to rewrite it if you want to, all right, to see maybe what some of the terms are. But let's see what this problem says. So here is this f of t. So we're using this guy to approximate f of t. And then it says g is the integral of that. Okay, so I'm going to have to take an integral. This I definitely want to rewrite because I try to get everything out as I can if I'm going to have to take an integral. So now I can see like the power part and the part that goes along for the ride. So now I'm going to do the integral of this. So this part's going to go along for the ride. And now I'm going to take the antiderivative to get to here. So it wants me to find the interval of convergence for this guy. I forgot to write this, sorry guys. Okay, so all of that's on the outside, and then I have this e to the 2n plus 1. So my interval of convergence, that that I want to look for where this is going to be. Oh my goodness. Okay, we've got a hodgepodge now. We would have to go and do this. And I'm going to stop. Is anybody like thinking anything on this one? Because I'm turning this into a lot of work. Because now I'm going to have to go do my ratio test. That part, absolute value, I don't need. 3. I mean, are you seeing like all of this work I'm going to have to go do? And then la 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 la. And you're like, oh my gosh, I thought this was geometric. I thought this was supposed to be way less work. Yes, it is. So let's discuss that. I'll go ahead and leave that up there, but because that's turning into a ton of work. Do you remember what I said? If we're looking at the interval of convergence, we are trying to find what is happening with these endpoints, right? And knowing like where we are centered. And we know we're centered at 0, and we can kind of like know that everything behaves the same except for the endpoints on the derivatives and the antiderivatives. So all the way back up here, from the very original, from this f, I know that I'm looking for where this guy right here, oops, this guy, not the n, is less than 1. And that's going to happen when t is in between 1 and -1. And all we have to do is go say now that this is like, for the original f, it's going to be the same for the other part, for g of x. I know that I'm going to have from -1 to 1, it's just that the endpoints could behave differently. So we need to just go check the endpoints into here. So I don't actually need to even go through all of this mess because I know it's going to behave the same way except for the endpoints. So we're going to go back to this one now and plug in the 1 and the -1 and see what happens. Okay. So let's go plug in. I need to get this down here so I can see. So I'm going to need to erase so I can actually see what's going on. Sorry, guys. Where I kind of like up and down. That's annoying. Okay. So we're going to go to this one right here, and we're going to plug in 1 and see what this gives me. So this is going to be 0 to infinity for -1 to the n, and I'm going to plug in 1 for my t. 1 to anything goes away, so I'm left with this. So now I can see that this is an alternating series. So I'm going to take the limit, as n goes to infinity, 4 over 2n plus 1. That goes to 0, bigger on bottom. And I can see that as I get bigger, that I am decreasing. So at 1, I converge. So now we need to go plug in a -1. So we're going to plug a -1 now into this. And -1 to the 2n is going to go to 1, so I just have -1 to the first. So this is almost exactly the same thing as what we saw before, except for it's a negative. So it's going to do the same thing, because the terms decrease in absolute value to 0. So this one actually gets both of them to converge for the integral. Okay? Okay, let's go to our next one. So this one wants a power series for arctan of x. Oh, arctan's like crazy. I don't want to take all those derivatives. So I do know something about arctan though. I know the derivative of arctan, 1 over 1 plus the x squared. Oh, and that makes me feel so much better now about what we're doing. So this is the little arctan trick. So now I know that this, well, it's approximately, is going to be my a over, sorry, it's going to be my a over 1 minus r, so I'm going to have my a times r to the n. So that is the same as -1 to the n, x to the 2n. And we could even think of that as like x squared to the n. Either way. Okay, so this is the derivative. So now I want to find an antiderivative of this guy. So now I'm just going to take the antiderivative here. So this guy goes along for the ride. And then I'm going to take 2n plus 1 over 2n plus 1, and then I have a plus c. And the plus c is what gets a little bit trickier, but it's always going to be 0 for us. We don't really have to do much with that, okay? Just know it's there, but it's always going to kind of be okay for us. So this is what we want. And I know that's not a great explanation. We can discuss it more if you really, really want to, but it's just at this level, it's okay to kind of think, okay, sure. Um, these are just kind of like with the derivatives and the integrals of what we've discussed prior with all the intuition. You're going to see these in textbooks and different things, and it's nothing crazy. It's kind of like just what you want to happen, okay? It's just, I put them on there to just show you, but you've kind of already been doing these, so don't worry about it. But just look at them, and if you want to look through them and ask me questions, you can. Okay, so the last one in this lesson, in this day that I want us to do is this entire AP problem, okay? All right, so here's my function f. It gives me the first 3 non-zero terms, and it gives me the general term, and then it also gives me the power series. And it says for all real numbers x, the series converges. For all real numbers x for which the series converges. So that's only for the x's where it converges. Does this equal f of x? Find the interval of convergence for f and justify your answer. So we have two options when we are looking for that interval of convergence. We either want to think geometric or ratio. And here I can see that this is geometric. My a is 1, and this is my r. So I can see my a times 1, a times r to the n. So on part A, if I want the interval of convergence, I know I'm looking for where my R is less than 1. And now I'm going to do some algebra. And since this is geometric, the endpoints are going to diverge, so it stays just like this, and we do not have to check them. Now, if you're not going to check them, you need to state why. You need to say that in geometric power series, the endpoints diverge, and then that's what you get. Okay, so make sure that you clearly state that somewhere. Okay, B wants me to find the sum of the series. So when I see the word sum and I know that I am geometric, I know that I want to go ahead and do my A over 1 minus R. Sorry, it's Amber Alert. Okay, so go ahead and do your A over 1 minus R when you see the sum. So I'm going to do my A over 1 minus my R. So that's what the sum is going to be. And I can rewrite that as 1 over negative x. And we're wanting to plug in, so this is what like f of x is. And it wants me to plug in what did it say? I'm looking. No, that's all. It didn't want me to plug in anything. It just wanted you to find the sum of the series. It just says that's where I'm centered. So that's good. So that is all we have to do on B. Just wants the sum. And then if it wanted any x, then I could plug it in. Okay, g is now the antiderivative, and it wants me to find g of negative 1/2. Okay, so the first thing I have to do is find the antiderivative. Well, you could either do it up here, or you could do it right here. So I'm going to take this antiderivative of this, I'm just going to put in a t value for what we just saw. So this is the negative ln of the absolute value of t evaluated from negative 1 to x. So this would be the negative ln of the absolute value of x plus the ln of the absolute value of negative 1, that's 0. So I get this guy, and then I plug in a negative 1/2. And you can rewrite this however you want, but you can leave it as well. So that's all. Okay, part D. H is now this guy. I see like some inside, so I'm kind of thinking I might do a chain rule, but let's keep reading. Find the first 3 non-zero terms and the general term for h about x equals 0, and then find h of 1/2. So let's see. H is this f of x squared minus 1. So I kind of have some options. It's not wanting me to derive or anything. It just wants me to go plug all of that in everywhere I see an x. So I knew that f was this guy. So I'm going to go ahead and just plug it into that. So that would be, h would be negative 1 over the x squared plus 1. I'm just going to do function composition. And then it says go find h of 1/2. And I could leave it like that if I wanted to. Okay, or you could simplify it if you wanted to. That is completely up to you. Okay. Let's see. I think that's the end of this day. So go ahead, ask me any questions if you have them, and if not, just let me know. All right, I'll see you guys soon.